After the asymptotic tests of the two-way MANOVA technique, we just take up a few exact tests, few in the sense that in the very few situations where we can apply the exact tests. As in the case of one-way MANOVA, we have seen that for some low dimensional cases where there we had been given the number of groups, that is the value of k were given there, for which we could use the exact test technique. Here also in a similar manner, we will try to list down a few situations where we can use the exact test technique in the two-way MANOVA analysis. Okay, so what we have is essentially we just denote by gamma 1 the degrees of freedom for the sum of squares cross product matrix due to the interaction effect or the factor 1 effect. So, that we can write that factor A effect due to factor A or factor B effect, whichever the hypothesis I am testing. So, essentially this means that this first degrees of freedom gamma 1, it is referring to the degrees of freedom for the case interaction effect. Essentially means I am testing the null H naught 3 against the alternative of H naught 3, or if I have the setup of testing the equality of factor A effects, I am testing the null H naught 2, and similarly for factor B I am testing the this is not H naught 3, the first one is H naught 1 in fact, and H naught 2 for factor A and H naught 3 for factor B. And the second subscript, the second DF, always refers to the degrees of the residuals or the error. And then the situations which we can pen down are these few situations where I have dimension p equal to 1, which means that essentially I have an ANOVA case and gamma 1 is greater than or equal to 1. So, this gamma 1 refers to whichever hypothesis I am testing, whether if I am interested in testing the interaction effect, then I have to look at the degrees of freedom of the interaction effect. So, gamma 1 pertains to that in that case, and then the test statistic is given by gamma 2 by gamma 1, 1 minus again this lambda star, you can very well understand will change with the hypothesis. So, we have, this is my table, I have 1 minus lambda star. Note that for H naught 1 hypothesis I have lambda A B star, for H naught 2 hypothesis I have lambda A star. This is how we have denoted the likelihood ratio criteria, and for H naught 3 I have lambda B star. So, if I am testing the null H naught 1, in place of this lambda star I am going to use this lambda A B star and so on. My gamma 1 will also change accordingly, gamma 2 will remain fixed. So, under null, so this is under null H naught, whichever one is coming. Similarly, for the second situation I have just one increase in the dimensionality of the data for p equal to 2, and if I have this gamma 1 anything greater than or equal to 2, I can use an exact test given by the statistic is given by gamma 2 minus 1 by gamma 1, 1 minus root of lambda star by root lambda star, and this is following an F distribution with twice gamma 1 twice gamma 2 minus 1 under the null hypothesis. If the dimensionality generally will be considering data dimensionality of higher order, say 3, 4 or even more, and in that case if this factor is reasonably small, in fact only 1 or 2, only on those situations we can go for the exact test. And in this situation, the third situation where we have p is greater than or equal to 1, gamma 1 equal to 1, I have the test statistic as gamma 2 minus p plus 1 by p, and then followed by 1 minus lambda star by lambda star, this following an F distribution with p and gamma 2 minus p plus 1 under the null. And the last case is when I have the dimensionality anything greater than equal to 1 and gamma 1 is equal to 2, I can use the test statistic gamma 2 minus p plus 1 factor in the denominator remains p, and I have 1 minus root of lambda star by root lambda star following an F distribution again with 2p and twice gamma 2 minus p plus 1. So, again I stress upon the fact that when we are using the exact test, we have the classifications according to the values of p, which is always fixed, that is the dimensionality of the data, but the next classification is according to the value of gamma 1, which is essentially the first degrees of freedom of the F statistic. So, this keeps changing as we change our hypothesis from H01 to H02 to H03, and along with this what changes is the likelihood ratio criterion lambda Wilks lambda lambda star. If it is the interaction effect, essentially we are testing H01, then we have to look into the degrees of freedom of the interaction effect, put that value for gamma 1, and in place of lambda star we must put the value of lambda a b star and then get our F statistic. If it is H02 for gamma 1, we will have to use the degrees of freedom for factor A, the first factor, and in place of lambda star we have to use lambda a star and so on. And when I am saying that the classification, the next classification is according to the first degrees of freedom of the F statistic, it means that the second subscript, that is gamma 2, that is basically the degrees of freedom of the residuals, that can be anything. Okay. So, this completes the exact test table of the two-way MANOVA. We have these many situations, they are listed for us, and now let us go to a data example, but here as in the case of one-way ANOVA we have discussed in details with the data. Here we are not going to take up the data. I am just going to give a data setup, a typical data setup, and try to give some interpretation, and we are not we will not be working with the actual data here. Okay, so here the example is of some chemical process which is called an evolutionary operation process. It is basically a process to extrude plastic film, okay, and while doing so, three variables of interest are monitored, and there are two factors of production that we have considered. Note that now we are talking about two factors of production because it is now two-way MANOVA, and each of the factors having some levels, 2 or 3 or more levels. And let us see how a typical data setup is in this situation where we can apply the two-way MANOVA technique. Okay, so the setup is something like a practical example for the two-way MANOVA. What we are looking at is in a plastic film extrusion technique called an evolutionary operation. Three responses, basically three variables of interest, were monitored, namely tear resistance, gloss, and opacity. So, these are typical characteristics of a plastic film, how tear resistant they are, how glossy they are, how opaque or transparent they are. So, the responses on these factors, these were measured in some way, in some units, and further two factors of production were considered. Those were at two levels of the factors. First one is the rate of extrusion and the second one is amount of an additive used in the process essentially. So, two levels of the factors. So, we can see two levels for each of the two factors. These are the rate of extrusion and the amount of an additive. The rate of extrusion having two levels, it can be anything like high or low rate, and the amount of additive used, again two levels, can be moderate or excessive, or it could be the permissible level or the beyond the permissible level, something like that. So, we have essentially two factors, each having two levels and then the measurements. If you recall, we have something more in the theoretical setup. We said that there are n observations for each of the A-B combinations. So, the measurements here also were repeated for 5 times at each combination of the factor levels. So, what do we know now? What can we write here without knowing the actual data? I have an idea about something at least. I have data dimension P is equal to 3 because we have 3 responses. The measurements on 3 variables, tear resistance, gloss and opacity. We have number of levels for factor 1. Factor 1 is the extrusion rate. For factor 1, say the extrusion rate. Here each factor has the same level, so no problem. Extrusion rate, this is number of levels, so this is equal to A and this is equal to 2 here, and similarly number of levels for factor 2, that is amount of additive. This we are using the notation B, so that is also equal to 2. Number of observations, number of independent observations at each combination is n, which is 5 here. So, we can sort of write a dummy MANOVA table. So, MANOVA table, if we had known the data or at least the group means or the sample variance covariance matrices, we could have completed the entire MANOVA table. So, this is a sort of a dummy MANOVA table where we have the sources of variation is due to factor 1, the degrees of freedom is A minus 1. So, this is 1. I have sum of squares cross product matrix for this, which I am denoting by A, and then I have due to factor 2, the degrees of freedom is B minus 1, 1 again. This matrix 3 by 3 matrices, I am denoting this by A, this one by B, and the interaction of two factors, interaction effect due to interaction of the two factors, that is A minus 1 times B minus 1, that is also 1, and this is AB. What is the total number of observations? Well, we have how many? 4 combinations and we have 5 observations each. So, I have 20 minus 1, that is 19 is the total degrees of freedom, and hence I am going to have 16 df for the residual, which can be otherwise checked also, because I know the degrees of freedom for residual is AB times n minus 1. Here A is 2, B is 2 and n minus 1 is, we have n is 5, so n minus 1 is 4, so that gives me 16. Okay, and this matrix is denoted by E, and this is the total variability matrix. And now if I am interested in testing the interaction effect, what I am checking is gamma 1 1 is equal to up to I have gamma 2 2. So, that is gamma 1 2 and gamma 2 1 coming in between against the null against the alternative hypothesis. I will use the criterion AB lambda AB star, which is given by determinant of the AB matrix by determinant of E plus AB matrix, and this is going to a slight change in this with some constant. I can use the asymptotic test, but what is suggested here is the use exact test. Which exact test can you use? Use the exact test for the p greater than equal to 1 and gamma 1 equal to 1 case, because I have the degrees of freedom for the interaction effect is equal to 1, and then therefore the test statistic is nothing but gamma 2 minus p plus 1 by p 1 minus lambda a b star by lambda a b star, and this is following the F distribution with p gamma 2 minus 2 p plus minus p plus 1 gamma 2 minus p plus 1 under H naught. Well, you can partially calculate this because we do not have the value of this gamma of lambda a b star. This is equal to gamma 2 is the residual degrees of freedom and p is the dimensionality of the data, and 1 is so this is giving me, this is 16 minus 3, so that is 13 plus 1, and I am getting 4, 14 and p is 3. So, 1 minus lambda a b star by lambda a b star. This is following F with 3 and 14 under, this is H naught 1 under H naught 1. So, if therefore, if observed value, that is this value, if observed F exceeds F 314 at 0 1, we reject H naught 1 at 1% level of significance. Now, if H naught is accepted, which means there is actually no interaction effect by between the two factors, that is the rate of extrusion and the amount of additive used, that is whether the rate is high or low, that there is no connection with the fact that I have to use the moderate level or high level of additive. If that is true, there is no interaction effect, I go for the next two hypotheses, that is I test H naught 2, which tests that alpha 1 equal to alpha 2, I have only 2 levels of the first factor, that is equal to 0, and I also test separately H naught 3, which says that beta 1 is equal to beta 2 equal to 0. So, for H naught 2, I use again, if you have to use exact test, so use exact test for this p greater than, with p greater than equal to 1 and gamma 1 equal to 1 in both the cases. Why? Because I have the degrees of freedom for both the factors equal to 1, because both have two different levels. So, that is 1 for both of them in both the cases, and the test statistic also remains the same, both the cases same, but the value of the lambda criterion that is changing. The lambda star in the first case is lambda A star, while in the case of H03 it is lambda B star. Okay, so use lambda A star for H02 and lambda B star in H03. So, this is the sort of the data setup, a typical data setup where we can apply the two-way MANOVA technique and bring out some significant conclusion about this chemical process. So, this sort, and we have not taken into account the actual data. It's going to be a little cumbersome, though the data dimensionality is 3, but still. So, this can be actually done in any computer software. What is important is to know the theoretical foundation and how to give the interpretation. So, with this we close our discussion on MANOVA, and our next topic is going to be on multiple correlation coefficient. Okay. So, that is our next topic, multiple correlation coefficient. It talks about the degree of association among all p variables. Now, here essentially we are dealing with a set of p variables. The data dimensionality is p, and we are talking about a degree of association among all these p variables. Now, if you think about the usual correlation coefficient, it is giving you a pairwise association. It is always correlation coefficient between x and y. So, that is a pairwise association talking about two variables only. So, it is association between two variables, and if we do the same thing here, we will be actually getting a number of such correlation coefficients. In fact, we will get about p choose 2 correlation coefficients, and still that will not give us the complete picture about the association among all the p variables. So, we have to modify our usual definition. I mean, we have to take into account something new. Now, again if you recall the usual definition of correlation coefficient, you see that the data dimensionality there is 2. We are talking about x and y, it is bivariate. Now, here how do we handle that? So, in multiple correlation coefficient, we say that we are measuring the association between x and say x one of them, say x 1 say, and the rest of them x 2 to x p, that is 1 in one hand and p minus 1 on the other. But how do we handle this p minus 1 dimensionality in the other group? Well, we consider a linear combination of these p minus 1 variables, and so reduce it to the data dimensionality from p minus 1 to 1, and then we talk about the usual correlation coefficient between x 1 and this linear combination of the p minus 1 variables, say some alpha prime x. This x contains x 2 to x p. So, now if this is the situation, now one may say that, well, from p choose 2 number of correlation coefficients, we are now talking about an infinite number of correlation coefficients, because there can be an infinite such choices of linear combinations. So, what is the multiple correlation coefficient between this x 1 and the other variables? So, what we do is we maximize this simple correlation coefficient, maximizing over the choice of alpha. So, now we have handled the problem of data dimensionality. We are essentially talking of two dimensional case now, x 1 and a linear combination of any number of variables. So, what we have is two variables, but that linear combination factor is also taken care of by considering the maximum correlation coefficient of these two variables. Okay. So, let us formally define multiple correlation coefficient. We say that, so before that let us just give the introduction to the setup. So, suppose x is a random variable with dispersion matrix. The mean vector does not have much role to play here. So, we have dispersion matrix sigma. Now, partition X, the dimensionality is P, and sigma as, I am saying that X has, suppose it has x1 and x2. Now, this is a scalar while this is a p minus 1 dimensional vector. Now, in this x1 I can have anything, I can have x1 or x2, any one of the p variables, right. So, instead of writing just x1, I prefer to write 1 within a bracket, meaning that this x1 may contain any one of the p variables, and consequently the other part, the other subvector p minus 1 dimensional subvector will contain the remaining. So, if this is x1, the first variable x2 will contain x2 to xp. If this is x2, then this will contain x1, x3 to xp, and so on. Now, then as we have partitioned X, similarly we must partition the dispersion matrix. Now, this is a p dimensional square matrix, and this is going to have the variance, say sigma 1 1. Strictly speaking, I should write in this way, but for simplicity's sake, let me write just sigma 1 1 for this. So, it essentially is the variance of the variable which is coming here. If this is x1, it is sigma 1 1. If this is x2, it is actually sigma 2 2, and so on. But instead of writing that, I am just writing sigma 1 1 for this, and then I have sigma 1 2. This is a row vector, sigma 1 2, a column vector, and a p minus 1 dimensional square matrix sigma 2 2. So, this is setup is for, or let us write notation of this setup is for x1 is equal to x1. So, if I have the first variable as the first member here, then I will write this sigma matrix as sigma 1 1 variance of x1, sigma 1 2. This is actually the covariance vector, the covariance of x1 with x2, x1 with x3, x1 with xp, and so on, and this sigma 2 2 is the dispersion matrix for all the remaining p minus 1 variables from x2 to xp, right. So, that let us write here variance of x1 is sigma 1 1, covariance of x1 and x2, that is sigma 1 2, and the dispersion matrix of x2 is sigma 2 2. Okay. And after that I write the between, again say in a general way I write between x1 and x2, this is a scalar while this is a vector, is denoted by, or if we do not want to create confusion, let us write x1, sorry, this is a scalar, and x2, well x2 is, again let us just write that this is, let us put it in a bracket, x1 say it could be any xi, and x2. So, if this is x1, this is nothing but x2 to xp, between x1 and x2 is denoted by rho 1 dot 2 3 to p. So, this is actually a dot coming after this breakup, 1 dot and 2, 3 up to p. So, these are coming a little below this point, okay. Is the maximum correlation coefficient between x1 and any linear combination alpha prime x2, say of x2 to xp. Okay. Just what I have said, that we consider the correlation coefficient between any one of them and the linear combination of the remaining p minus 1 variables. We consider the maximum over this choice of the scalars which we are using for the linear combination alpha prime x2, basically for a particular choice of alpha, the maximum over the alpha, and that gives me the multiple correlation coefficients. So, our notation is, that is, we are using this by rho 1 and 2, 3 to p is given by covariance. Then what comes is the usual definition of correlation coefficient. So, we have covariance between x1 and the next scalar valued variable, that is alpha prime x2, not a problem. And then what we have is standard deviation root of variance of x1 times root variance of alpha prime x2. This also comes in a bracket. So, we have a typical bivariate correlation here. We have reduced the dimensionality, and then what we have to consider, we have not left any space for this. So, this is rho 1 dot 2, 3 to p. This equals maximum of this simple correlation coefficient, the maximum being taken over alpha. Alpha is having the same dimensionality as x2 bracket, that is p minus 1 vector. You can take the maximum over any choice of such vector. Okay, so, this gives the multiple correlation coefficient. What is the covariance between x1 and alpha prime x2 according to our notation? So, basically we are going to consider maximum over alpha, the covariance between x1 and alpha prime x2. So, we have to look at the sigma matrix. So, what is this according to this notation? Again we come back to this notation, and this is nothing but we have alpha prime and then covariance between x1 and x2, which is sigma 1 2. Variance of x1 is root of sigma 1 1, and variance of alpha prime x2 is nothing but alpha prime sigma 2 2 alpha. So, we have to essentially maximize this correlation coefficient, this measure of correlation coefficient with respect to this alpha, which is coming here as well as it is coming here. So, for this purpose we are going to use a very common inequality used several times in statistical analysis, namely the Cauchy-Schwarz inequality. Use Cauchy-Schwarz inequality given by, in the vector form, you have, if you have two vectors u and v, I have the scalar product is less than or equal to product of the norms, and we have u transpose u raised to the power half. Similarly, v transpose v raised to the power half. So, this is the one we are going to use, and what we do is take for typical particular choice of u and v. So, it's almost apparent from the expression of the correlation coefficient what we have written. So, we take u as sigma 2 2 half and then we have alpha. Both, it is not a problem of conformability because we have a p minus 1 dimensional matrix here and a p minus 1 dimensional vector here. So, no problem, and V as sigma 2 2 minus half with sigma 1 2. So, again no problem, this is p minus 1 dimensional square matrix, this is also p minus 1 dimensional vector. Note that these square root and the inverse square root matrices are defined since sigma 2 2 is a dispersion matrix, and we can use the spectral decomposition of sigma 2 2 to obtain what is sigma 2 2, the square root matrix of sigma 2 2 and the inverse of square root of sigma 2 2. Because we have non-zero, in fact we have positive eigenvalues for sigma 2 2. Okay. Now, with this choice of u and v, we directly apply the Cauchy-Schwarz inequality to get, we have then from the expression I have, what was it? So, it is rho 1 dot 2 3 up to p, and this was max of over alpha, alpha transpose sigma 1 2, and then we had root of sigma 1 1 alpha transpose sigma 2 2 alpha. Okay, so just recall this. So, by definition we have got this, the multiple correlation coefficient. So, what we consider here is alpha prime sigma 1 2 and try to give an upper bound to that using the Cauchy-Schwarz inequality. So, we have root sigma 1, this is less than or equal to, because what we have here essentially with this choice of u, choices of u and v, what we have here is essentially u transpose v, and then this is less than equal to u transpose u, which gives me alpha transpose sigma 2 2 square root, and then root of that, and we also have v transpose v and root of that. So, we have here sigma 2 2 in square root inverse of that and sigma 1 2. So, this is u transpose u, we have to write this again with, it is better to write the full form, right, with the half notation. So, that we have alpha transpose sigma 2 2 half u transpose u sigma 2 2 half and alpha, this with the half, and then we have v transpose v. So, that is sigma 1 2 half sigma 2 2 minus half. These are symmetric matrices. So, I am just repeating the matrices without the transpose sigma 1 2. This also have a root, and this is as it is alpha transpose sigma 2 2 alpha. So, we are going to reduce this to the form to get the upper bound of the multiple correlation coefficient. Now, note that this is due to the fact, because we have, since alpha prime sigma 1 2 is nothing but, what we are doing is bringing in this sigma 2 2 half and sigma 2 2 minus half matrices into the picture to use the Cauchy-Schwarz inequality in this form. So, this has been replaced by this first, and then this, the inequality has been used. Now, what we have at this stage after simplification is nothing but, note that this alpha, this variance term actually cancels out with this, and what remains here is sigma 1 2 transpose with sigma 2 2 inverse defined. So, not a problem, and sigma 1 2, and I have a sigma 1 1, this goes away, cancels away, but this whole thing raised to the power half. So, equality, when there is equality in the Cauchy-Schwarz inequality situation. So, when this, well, when u is equal to v, so we have when sigma 2 to half and alpha is equal to sigma 2 to minus half and sigma 1 2, right. That is, I have a choice of alpha. This alpha is nothing but sigma 2 to inverse sigma 1 2. So, this particular choice of alpha gives me the maximum correlation coefficient, and the value of the maximum correlation coefficient is given by finally by this expression, which you see is free of alpha. So, not a problem. This is the value of the correlation max giving me. So, implying rho 1 2 3 to p is equal to, because that is the maximum value of this. So, that is sigma 1 2 sigma 2 to inverse sigma 1 2 sigma 1 1, right. Now, we know that the usual correlation coefficient between x and y, it always lies between minus and plus 1. Let us see what happens to the multiple correlation coefficient. Does it have the same bounds or is it something different? So, for that we note some things. So, we are few important notes after the definition. The first one, note that if you consider the variance of the variable, scalar valued variable. Now, what we had started with was a linear combination of the remaining variables. So, we had started with some alpha prime x 2, and the choice of alpha that we got for maximizing the correlation coefficient was sigma 2 to inverse x 2, right. So, if I consider variance of alpha prime x 2 for this choice of alpha, what do I get? So, essentially I am considering variance of sigma 2 to inverse sigma, sorry, that is not x 2, but sigma 1 2, right. So, that is sigma 1 2 transpose. So, this is the particular choice of alpha transpose x 2. Now, this variance is nothing but, I have to consider the dispersion of this. So, this is basically variance of sigma 1 2 transpose sigma 2 2 inverse transpose, that is transpose inverse. So, basically we are getting inverse only, and x 2. So, that is giving me sigma 1 2 transpose sigma 2 2 inverse dispersion matrix for x 2, that is sigma 2 2, and then again transpose of this whole thing. So, that is sigma 2 2 inverse and sigma 1 2, which is sigma 1 2 prime sigma 2 2 sigma 1 2. So, what I see is the correlation coefficient, the multiple correlation coefficient 1.232 p is nothing but variance of, which is again recall, which is this one by sigma 1 1 root half, is actually the root over of the ratio of two variances. The first variance is in the numerator, it is the variance of sigma 2 2 inverse sigma 1 2 transpose x 2, and the denominator is variance of the separated out variable x 1 raised to the power half. So, this implies that although the usual correlation coefficient lies between minus 1 and plus 1, and although we have used more or less the same techniques, the same thought process to obtain the multiple correlation coefficient, still the multiple correlation coefficient lies between 0 and 1. It cannot be negative, and it is lying between the other part is we are getting another sharper bound for this. So, giving me the value of rho 1, 2, 3 to p this part, the other part of the inequality is quite obvious. Again, it comes from the Cauchy-Schwarz inequality. Whichever applies for the simple correlation coefficient, the same logic will apply here to get this part of the bound, but for this part we are using this the reasoning which we have just stated, because it is the ratio of two standard deviations essentially. Okay. After the bound, let us talk about some interpretation of some other interpretation of the multiple correlation coefficient. Suppose you have, let us consider the correlation coefficient between two scalar random variables. So, that is x1, and now we are basically considering the linear combination that is my second variable which I have used. So, that is first one is x1, the scalar valued random variable, and the next one is alpha prime x2, but with the typical choice of alpha, this particular choice of alpha. So, that is sigma 2 to inverse sigma 1 2 transpose x2. So, I am considering correlation coefficient between these two variables, and this is giving me essentially, well, what is this? I have covariance between x1 and covariance between x1 and sigma 1 2 transpose sigma 2 to inverse x2, and here I have variance of x1 with variance of sigma 1 2 transpose sigma 2 to inverse x2. I have already obtained these expressions. So, this was sigma 1 1, and I saw that this variance is nothing but the root of this variance. It is sigma 1 2 transpose sigma 2 to inverse sigma 1 2, and this is nothing but sigma 1 2 transpose sigma 2 to inverse, and covariance between x1 and x2, that is sigma 1 2, and I am getting the multiple correlation coefficient between x1 and the other remaining p minus 1 variables. So, that is sigma 1 2 and sigma 1 2 here and sigma 1 1 here, the root of this. So, basically the multiple correlation coefficient that I have obtained is nothing but the simple correlation coefficient between x1 and this linear combination of the other p minus 1 variables, namely it is the simple correlation coefficient between x1 and sigma 1 to transpose sigma 2 to inverse x2, where these matrices, these parameters have the usual interpretation. This will vary accordingly as I vary my basket of x2 variables, so that I get a different xi. I consider a different xi each time the other basket will change, and similarly consequently the composition of the dispersion matrix, the original dispersion matrix sigma will change. So, I will have sigma I the first element, and in this way. This can be handled very easily. The third point that we consider is, suppose I have x is following the p-variate normal distribution with mean mu and dispersion matrix sigma. I have mu also partitioned now as mu, my partition of the x vector, the random vector remains the same as before. I consider a single one here x1 and x2, So, accordingly mu is mu1 and the rest of it, and sigma is sigma 1 1, sigma 1 2 and sigma 2 2. So, obviously, if x1 is nothing but the first random variable x1, then mu1 is also equal to mu1, and this holds for any I, and accordingly this also is changing. Okay. So, if this is the situation, what is additional here is this distributional assumption of multivariate normality, and we have already seen that the conditional expectation of x1 given x2. Now, let us specifically consider this the first random variable as x1. So, I am writing it without the bracket. So, this x2 contains the usual x2 to xp. So, this conditional expectation is nothing but mu1 plus sigma 1 2 transpose sigma 2 2 inverse, then it is x2 minus mu 2. If you recall our earlier discussions on multivariate normal distribution, this will come immediately, and variance, the conditional variance of x1 given x2 is nothing but sigma 1 1 minus sigma 1 2 sigma 2 2 inverse sigma 1 2. And let us use a special notation for this conditional variance. Let us write this as sigma 1 1 dot 2 3 up to p. And then if I consider the correlation coefficient between x1 and the second random variable that I consider here is a particular choice of x2, but that is not the usual choice of x2 that we have been considering all along till now, but the second variable is in fact here that I consider is the conditional expectation of x1 given x2. Note that this conditional expectation is nothing but a linear combination of x2. So, let me consider the correlation coefficient between x1 and this second variable, which is expectation of x1 given x2. That is another linear combination of x2. Now, what is this? This is giving me, put a question mark here, I am trying to find what is this equal to. Okay, so, for this first I have to look into the covariance of between these two variables. So, that is x1, expectation x1 given x2. Let me write what is this conditional expectation specifically. So, that is mu1 plus sigma 1 2 transpose sigma 2 2 inverse x2 minus mu 2, right, and this gives me for the first term x1 and mu 1, that is 0, because this mu 1 being a constant. So, what will I have is for the second term, that is x1 with this term sigma 1 2 transpose sigma 2 2 inverse and so on. So, that gives me sigma 1 2 transpose sigma 2 2 inverse. Note that I am considering the covariance of x1 with this expression. Again, if whether I consider it with the whole thing or just this thing, it is immaterial, because even if I separate out this mu 2 factor, again I am going to get a 0 covariance, because this part will consist of only constant terms. So, I have the dispersion matrix of x2 only, and that is sigma 2 2, and I have sigma 2 2 inverse and sigma 1 2 here. Sorry, this is not in this way, but what I am getting is sigma 1 2. I am considering the covariance between x1 and sigma 1 2 transpose with sigma 2 2 inverse x2. So, I have sigma 1 2 inverse with sigma 1 2 transpose sigma 2 2 inverse and this covariance. So, that is sigma 1 2, basically the same thing is coming, but more easily. And what I have next is implying that correlation coefficient in that case is equal to correlation coefficient between x1 and the conditional expectation of x1 given x2, and that is equal to the covariance is sigma 1 2 transpose sigma 2 2 inverse sigma 1 2, and the variance is sigma 1 1, and the dispersion of this matrix, which is nothing but we are considering the dispersion of this variable. For mu 1 I have no contribution at all, and then this part is giving me sigma 1 2 transpose sigma 2 2 inverse sigma 2 2 and sigma 2 2 inverse with sigma 1 2. So, that is being equal to nothing but the usual correlation coefficient between 1 and 2 p variables, my usual correlation coefficient. So, we are going to continue. We have seen for the multivariate normal case, the multiple correlation coefficient has an extra interpretation, that it is the correlation coefficient between x1 and the conditional expectation of x1 given x2. With this we are arriving at the same multiple correlation coefficient between x1 and x2 to xp. So, we shall continue from this.